Electrons behave like waves because they're described by a wave function. That's what I used to believe, but that's not true. Electrons are not physical waves. The wave function is not a wave in space. What do I mean by that? And if that's true, why do we call it a wave function? Hi, I'm a physicist and this is what the wave function actually is. In quantum mechanics, we describe fundamental particles with a function called wave function. Spoiler alert, it does not look like this. It got this name due to historical reasons. This is something that often happens in physics. Things get named a certain way and then the name just kinda sticks, regardless of whether it turns out to be good or not. I feel like this is something we don't pay enough attention to, because how we talk about things influences how we think about them. I used to think a wave function referred to an actual wave, and in my head I pictured electrons like water waves. I'm not saying this picture can't be useful at times, just that we have to remember that it's not literally reality. Quantum mechanics does not say that electrons are physical waves, like sound waves or water waves. But now you probably say, but electrons can do wave stuff. They can interfere with themselves, they even have a wavelength. And you're right, you can see phenomena like interference happening for electrons. And using these phenomena you can calculate a wavelength. But you can only reveal them if you look at a lot of electrons. In the double-slit experiment, for example, you shoot a lot of electrons to produce an interference pattern. Now you might say, so what? We simply can't measure an electron being wavy because as soon as we measure it, it becomes a particle. But still, we get a wavelength and wave phenomena. So what's the difference between this and a physical wave? For a physical wave, the wavelength and wave phenomena would be the result of an oscillating medium. Water waves, for example, are happening because the water is moving up and down. The movement of the water gives you a wavelength and things like interference. The water is a physical medium that is oscillating. You can measure this oscillation. But in the case of an electron, in quantum mechanics there is no physical medium going up or down. So quantum mechanics does not say that the electron is physically oscillating. But quantum mechanics also says that there is indeed something that oscillates. What? And where do the wave phenomena come from? We'll get there. But first, let me try to convince you that the wave function does not correspond to a physical wave. And then we'll see how the wave function actually looks like, where it comes from and what it tells us. Okay, so maybe there's no medium oscillating like water, but still we describe an electron with a wave function. I mean, if someone said to me, here, that's a particle, and it's described by a thing called wave function, I would immediately have a picture like this in mind. This is a classical wave function. Spoiler alert, this is only half of the story, but let's stick with it for now. So, we have one particle, one wave function, whatever this function might look like. We usually draw wave functions as depending on just one direction because it's easier to visualize. But actually this function depends on the particle's position and time. So you have one variable for each direction in space. But still, without further detail, I would kind of picture this as a wave in space. But now let's add another particle. How can we describe two particles? With two wave functions? Well, actually, we describe them with one wave function. This new wave function now depends on the positions of both particles. So this function has 6 space-like dimensions. And I really cannot draw it, because I know, crazy news, we live in a 3-dimensional world. So a thing that is 6-dimensional cannot exist in our 3-dimensional world or our 4-dimensional space-time. It exists in a mathematical space called a Hilbert space. Importantly, whatever the wave function is, it cannot be a wave in our 3-dimensional space. By the way, that's actually the reason quantum entanglement exists. Entanglement is this thing where you, for example, measure the spin of one particle and you immediately know the spin of the other particle, even if the particles are incredibly far apart. Two entangled particles are described by the same wave function. If you measure one of them, you change the whole wave function and therefore also the state of the other particle. Okay, so the wave function of multiple particles cannot exist in our spacetime because it simply doesn't fit. It depends on too many dimensions. But what if you go back to one particle? One space dimension. Is this wave somehow a physical thing living in our spacetime? No. And this brings us to how the wave function actually looks. In a simple case, you can visualize the wave function like this. What is this? First, you may notice that this function has two parts, here and here. and this thing in the middle is somehow the sum of them. Both these parts just look like ordinary classical waves. So calling it a wave function is actually not unreasonable, because the quantum mechanical wave function is somehow the sum of two wave functions. But one of those wave functions is multiplied with an I. You probably heard about the imaginary number, and you know that this is important for doing math, but it has no correspondence in real life. You can have 1, 2 or 3 apples, or even 3/4 of an apple, but you can't have I apples. A physical quantity always corresponds to a real number. You can only measure real numbers. But the wave function is a complex number, because it contains this I. So it cannot be a physical quantity, in the sense that you cannot measure it. If you're familiar with complex numbers, you know that you can split them into a so-called real and an imaginary part. Both parts are like classical wave functions, but the imaginary part is multiplied with an I. So, this axis shows the value of the real part and this the value of the imaginary part. And the middle thing tries to visualize the resulting complex number. So the thing that's really oscillating are the parts of the wave function. But this is a mathematical thing. They are oscillating in a mathematical space. These axes are not directions in our three-dimensional space. In fact, this function still only depends on one space-like direction. Furthermore, it depends on things like a wavelength. This is the wavelength we've been talking about earlier. So if people talk about the wavelength of an electron, they are actually referring to the wavelength of the electron's wave function. The wave function is the thing that is oscillating, so only the wave function has a wavelength. People usually just say the wavelength of an electron because they're lazy, and because you can relate this wavelength to a measurable physical quantity. You can relate the wavelength of the wave function to the particle's momentum. This way, you can associate a particle with a wavelength. So, this is a better way to picture the complex quantum mechanical wave function. A function that oscillates in an abstract mathematical space. Alright. I hope by now I convinced you that the wave function is nothing physically real in the sense that it's not measurable. And I also hope that I convinced you to like this video. Thank you, it helps a lot. Now you might say, but the wave function describes something physically real, namely particles. How does that fit together? Why is it complex in the first place? And what is the wave function actually? Even though the electron is not physically oscillating, we see wave behavior if we observe electron distributions. To describe that, physicists use the wave function. Quantum mechanics doesn't tell us what the electron is, it only gives us ways to describe electrons. The wave function is complex, but if you square it, you get something real. You get a probability distribution or probability density. What is a probability distribution? To explain that, let's look at the interference pattern of the double-slit experiment. You probably know this experiment. Shoot electrons at a screen but place a barrier in between, such that they can only go through 2 slits. And then look at the patterns appearing on the screen. That's the double-slit experiment, simplified. And this is roughly the pattern you'll see on the screen. More dots mean more electrons hit there. Fewer dots means fewer electrons. We can stack the dots that landed in the same region on top of each other and get this wave shape. Now, an area below this wave corresponds to the dots we just stacked. Let's say there are 100 dots, then this area gives us the probability of an electron landing there. So, the areas under this wave give us probabilities, and this wave corresponds to the square of the wave function. So, the squared wave function is a probability distribution because it tells us how likely it is that we will find an electron at some place. So, the wave function is a basis for calculating probabilities of measurement outcomes. Even though the wave function is not measurable itself, it perfectly describes measurable phenomena, like interference. How? To understand that, we first need to know where the wave function comes from. In quantum mechanics, you describe a system with a Schrödinger equation. It can be different depending on the system. Importantly, this side of the equation asks, how will the system change over time? And this side somehow has the answer. You can compare this to Newton's force equals mass times acceleration. Here, this side asks, how will it change over time? And this side has the answer. If you solve this for psi, you get the wave function of the system. Maybe you've already noticed the I in the Schrödinger equation. That's where the I of the wave function comes from. Furthermore, the Schrödinger equation has one important mathematical feature. If you have 2 valid solutions, the sum of those must be a solution as well. That's what we call a superposition. A wave function that is the sum of two wave functions. The wave function that corresponds to the probability density of the double slit is actually such a sum. It is obtained by adding the wave function for electrons passing through the first to the one for electrons passing through the second slit. Importantly, to calculate the overall probability distribution, you first add the two wave functions together, and then you take the square. This way, the probability distribution contains this additional term. This interference term drastically shapes the probability distribution. So, to calculate wave phenomena, you first work with the wave function, and only in the very end you take the square of it. If the wave function weren't complex, it actually couldn't explain both wave phenomena and probability correctly. Classical waves go up and down, and that's why we can do wave stuff. But this also means that they are zero at certain points. But if the wave function is zero, it's square, and therefore the probability would also be zero. But the two parts of the wave function are shifted relative to each other. If the real part is zero, the imaginary part is not. This way, the quantum mechanical wave function can do wave stuff without ever crossing zero. Okay, so the wave function lets us make calculations and predictions. But is it more than that? Well, at first, the wave function is basically just a mathematical tool used to predict the probabilities of different measurement outcomes. Whether the wave function is actually something real beyond that is kinda up to debate. Different interpretations of quantum mechanics answer this differently. What do you think? What makes more sense to you? Please let me know. Because there are people that argue that the wave function is just a summary of our information, so it's a human construct, a mathematical tool, and the famous collapse of the wave function is nothing more but an update of our knowledge. On the other hand, there are people that say that the wave function is a physical objective thing, so it's something that somehow exists independently of us. And the collapse is somehow a physical process. In the many worlds interpretation, for example, the collapse is not really happening. The wave function just splits up into different branches. Okay, so in quantum mechanics we describe electrons with wave functions, but quantum field theory actually tells a different story. Check out this video for more. Thanks for watching. Have a wonderful day.